All right, hi everyone. So this is the solution video for the April 13th worksheet. And these are all addition reactions. So once again, here's an addition of HCl to an alkene. And remember, we do need to consider the number of H's that are bonded to each end because of Markovnikov's rule. So in this case, we would expect there to be two products from this reaction, right? One where the H of the HCl got added to the right-hand end, and the chlorine to the left-hand end. And then a second product where the H got added to the left end and the chlorine to the right end. And both of those are reasonable products, right? This one does not have any chirality centers, but this one, however, does have a chirality center right there. And so this one is going to be the 50-50 mix or racemic. Okay, now in terms of which one is the major product, let's look at the mechanism of this quickly to find out. Okay, so the first step again is nucleophile here, electrophile there, and Cl minus leaves. So what we have after that again is two possibilities, right? We have the possibility where the H adds to the right-hand end of the alkene, and our carbocation is here, right? Again, that's one possibility. Okay, there's our plus charge. Or, again, those same arrows could lead to a second one where the H adds to this end, and our carbocation is here. Now, this one is secondary carbocation, right? There's a carbon, and an H. This one, there's a carbon, and a carbon. So this one is tertiary, okay? And then don't forget, we still have our Cl minus here as well, right? That was produced from that arrow. So both of these are okay, they can happen, but again, the tertiary is more stable than the secondary. So right there, we know that this is going to be the major product. And again, it's because this cation, this tertiary one, is more stable. And this one then again would be the so-called minor. And again, we don't know exact amounts. There could be 20 or 30% of this and 70 or 80% of that, something like that. Okay, now as far as the mechanism, well, again, this one could form a bond here, which would lead to our major product, right? Or, right, I guess maybe I can get the blue out here now. Or that same chlorine could form a bond to this one here, in which case we would then get our minor product over there, okay? So, and again, this happens from both sides because that's flat, so that's where our 50-50 mix or our racemic mix is up here. So maybe I should say racemic. Okay, so there it is, right? So not so bad, right? So two products. This one is a racemic mixture. Here's the mechanisms for both kind of drawn at the same time. And you'll see that all of these, once you do a few of them, start to look very similar to one another. Okay, the next one is also a straight chain molecule. Very similar to the previous, except now our alkene is over on the right-hand end, right? And in this case, we're going to add HBr to this one. And the question is, what are the products? Well, again, we have several H's here on our original molecule. So you would think, again, Markovnikov's rule, H for this HBr would go here, so the bromine would go there. And that is, in fact, one of the products. Right, we add the third H to this end carbon, and then the bromine to this middle carbon here. And once again, that is a chirality center, so this again is going to be the 50-50 racemic. Now, we don't, however, add the H to this middle carbon, because that would give us a primary carbocation out on the far end, which is so unstable it does not form, okay? That, however, is not the only product, okay? Let me start the mechanism and I think we'll see what happens. So again, alkene is the nucleophile, H is the electrophile, right? So from those arrows, what we get, again, the H adds to the right-hand end. Our carbocation is here, and we have Br minus. And just to emphasize again, in theory, those same two arrows could lead to this one, where the H goes to the middle, but this is a primary cation. Oh, this one is secondary, okay? And remember, primary cations do not form. They're so unstable that they just are not useful for reactions. Okay, so we don't have to consider that. Okay? However, if we look just next door over here, this carbon to the left has a methyl, and an H. If we do a rearrangement where this H with its electrons moves over to that point, what we then have, again, our original hydrogen from our HBr added to the end, we still had an H here, and now we rearranged another H to there, and our cation is here, and this is now tertiary. That's even better, right? Remember, that was one of the criteria where rearrangements occur. If a secondary becomes tertiary by an H or a methyl group rearranging. So now, what we have for our final step, right, is this bromine could form a bond to that cation, and that is not this product. So there is actually a second product here as well. Which is that one right there, okay? And this one, again, does not have any chirality centers. So we have 50-50 racemic here, and one with no chirality centers. Now, with respect to which one you're going to get more of, tertiary is always better. So even though that needed to rearrange, this bottom one is going to be the major, and this top one is going to be the minor. Oh, and I guess I should have put my other arrow in here, or this bromine could form a bond to this cation here before it rearranges. So that would give us our top product, and if it formed a bond to that one, that would give us our bottom product. So again, the fact that this has to rearrange to become tertiary, that's still the major product. That doesn't affect really anything at all. Okay, so there's a good one. And then the last one is a cyclic compound, but it's really the same problem as the first one. It's just with a somewhat bigger organic molecule. So I don't want you to get confused by the fact that you may have lots of extra. All right, so the third question here is this cyclohexene with HI getting added to it. And again, if we look at this structure, this is going to be very similar to the first one. So I don't want you to get confused by the fact that it looks like there's a lot of other carbons. So if I just do a quick erase right there, take the back half of that ring off, that is exactly the same molecule and same setup as you had in the first question. Right? There's one H here and no H's up at the top. So the fact that this ring is here really has very little impact on the reaction. Now, again, Markovnikov's rule would say the H would go to the bottom carbon of the alkene down here, and your I would go to the top. And that you would expect to be the major product, very likely. And then the other option in this case is still also possible, where the H goes to this top one, and the iodine goes to the bottom carbon. And this, of course, is a chirality center, again, that we generated. And technically, this is a chirality center too. But at least with respect to this, it's a 50-50, right, racemic mixture for that one. And again, it gets a little more complicated because of this chirality center as well. But if we think about our mechanism, it's exactly the same. There's our two arrows, and what we would get from that, again, we would expect from Markovnikov's rule that H would go there to give us a tertiary cation, or we could also potentially have, right, the H going here and giving us a secondary cation. Now this one is less stable, it's not as good as that one with respect to our reaction, but that then tells us that, in fact, we were correct, that this should be the major product, the one that follows Markovnikov's rule. And this is going to be the minor. And again, 50-50 racemic for this chirality center that we generated, and things get a little more complicated because of that. And again, don't forget we have our I- here yet, so we could complete our mechanism. So that I minus could form a bond to this position, and that gives us our major product up here. Or, right, the I minus could form a bond to this position, and that would give us our minor product down here. And again, it's 50-50 with respect to the chirality center marked in red, but because this top one is also a chirality center, it gets a little more complicated. So you'd have to consider that as well, and that's something a little beyond what we're going to do, at least for this chapter. But the idea is this question and the first question with the smaller straight chain molecule really are exactly the same concept. And when we start to get to hydrations, which is for next time, you will see an awful lot of similarities to these HX additions as well. We'll see you then.